Okay, so as I was saying, in order to get the I out of the denominator, we need to multiply our complex number by its conjugate. So what I mean by a conjugate is that if I have the complex number a plus bi, it is the same real and imaginary terms, but with the opposite sign in the middle. So a minus bi would be the complex conjugate to a plus bi. So let's go ahead and do an example where we have to use this. Let's say I have the function 5 over 1 plus I, and I would like to simplify this. This means I have to get the I out of the denominator. The only way to do that is to multiply both the numerator and denominator by the complex conjugate, which here is going to be 1 minus I, because it's the same real and imaginary part with the opposite sign in the middle. We have to multiply both the numerator and denominator so that we don't change the value of our equation at all. From here, I just go ahead and multiply straight across. 5 times 1 is 5. 5 times a negative I is negative 5I over. In the denominator, we need to FOIL. 1 times 1 is 1. 1 times a negative I is a negative I. I times 1 is a positive I. And then I times a negative I is a negative I squared. It's pretty cool because our negative I and our positive I cancel each other out. I also know that I squared becomes a negative 1, so this becomes y minus a negative 1 in the denominator, which simplifies to 1 plus 1, which is 2. So this becomes 5 minus 5i over 2. I can't leave it like this still because a complex number is separated, so it's two different terms, which means I'm going to need to write each of these as a fraction over 2, and then I'm finished. So it becomes 5 halves minus 5 halves I. Let's go ahead and do another example just so we get in the practice of doing this a little bit more. Let's say I have the complex fraction 5 plus 2i over 3 minus 2i. Again, I would like to simplify this as far as I can possibly go, which means I'm going to need to get the I out of the denominator. As before, the only way to do this is to multiply the numerator and denominator by the same real and imaginary part, but with the opposite operation, or its conjugate. From here, I just go ahead and multiply straight across. I'm going to have to FOIL both the numerator and the denominator. 5 times 3 is 15. 5 times 2i is 10i. 2i times 3 is 6i. 10 plus 6 is 16i. 2i and 2i becomes 4i squared over, same thing in the denominator, 3 times 3 is 9. 3 times a 2i is a positive 6i. Negative 2i times 3 is a negative 6i, so those are going to cancel each other out, which leaves me with negative 2i times 2i, which becomes negative 4i squared. From here, I go ahead and continue simplifying. Really, the only thing I have left to do is to replace the I squareds with negative 1s, which means I'm going to have 4 times a negative 1, which makes this a minus 4. In the denominator, I have negative 4 times a negative 1, which makes this a plus 4. I go ahead and simplify. 15 minus 4 is 11, plus 16i are my numerator values. 9 plus 4 is 13 is my denominator value. And the last thing I want to do is split it into two terms. So I have 11 over 13 plus 16 over 13i. So that is how we multiply by the conjugate of an imaginary denominator. We're going to go ahead and do one more just because it's really good practice, and then we'll move on to the next part of this. So let's say I have the fraction 2 plus I over 3i. This one is a little bit different because my complex number in the denominator only has one term. It doesn't change the fact that I still have to get rid of my I term, which means I'm just going to multiply by what the denominator is. So I'm going to multiply both the top and bottom by 3i. If you wanted to, you could multiply by negative 3i. It's not going to change anything because my I is still going to go away. I go ahead and I multiply straight across. I get 6i plus 3i squared over 9i squared in my denominator. I squared, remember, is negative 1. So 9 times a negative 1 becomes a negative 9. 3 times a negative 1 becomes a negative 3. I simplify from here. I get negative 3 plus 6i over negative 9. I need to separate this into two terms. So I have negative 3 over a negative 9 plus 6 over a negative 9i. Negative 3 and negative 9 reduce to a positive 1 over 3. 6 and 9, I can pull a 3 out of each of them, and I get 2/3, and it's minus because there was a negative there. And then the I gets attached to that 2/3 term. So what I want to do now is I want to take all of this imaginary stuff that we've learned, and I want to use it to solve some equations. So the first one I'd like to solve is 3x squared plus 48 equals 0. We've kind of done a little bit of this already in the examples, but it never hurts to do a little bit more. So from here, to solve it, I'd like to isolate the x term, so I need to subtract the 48 across. Divide each side by 3, and then square root both sides. When I do, I get x is equal to the square root of negative 16. As we already know, we can't take the square root of a negative, so I need to take the negative out by placing an I out in front. And then I reduce the radical as much as possible. The good news for us is the square root of 16 comes out to be a whole number, which is 4. So I get x is equal to 4i. But it's not just 4i when I'm talking about an equation, is it? Because it's not just positive 4 times positive 4 that gives us a positive 16. It could also be negative 4 times a negative 4, which gives us a positive 16. So when I'm talking about it in terms of an equation, I need to include both the positive and the negative versions of my square root. Let's go ahead and do another one just as practice. So I have 2x squared plus 10 equals 0. Just like before, I'd like to isolate my x term, so I need to subtract the 10 across. Divide by 2. Then I'm going to square root both sides, and I get x is equal to the square root of negative 5. I can't take the square root of a negative, so I need to put the I out front and make it positive. I can't take the square root of 5 because there is no perfect square that comes out of it. So I would just write this as x equals the positive negative versions of I root 5. So even though I wasn't able to simplify that square root, I still have to accommodate for both the positive and the negative versions of it. Okay, there is another example on there if you would like to do it. I don't really feel like it's necessary, but it's good practice for you. So now we're going to talk about solving for values that make my imaginary numbers or complex numbers true. So solving for x and y so that our equations are true. And this is really the last portion of notes we're going to do for complex numbers, which is good because I only have 6 minutes left. So what I mean by this is if I have an equation, let's say, for example, 9 plus 12i equals 3x plus 4yi. I know these two are equal to each other because that's what my equal sign means, but I don't know what x and y are, so I need to figure out what they are so that I can prove that they are in fact equal. When we do this, it's very similar to how we combined or added and subtracted complex numbers. I'm going to set equal or same parts equal to each other and then work backwards to solve for my variables. So here my two real parts are 9 and 3x. So I'm going to say 9 is equal to 3x. But I don't just have real parts in these complex numbers, right? I have the imaginary portion. So here I have 12i is equal to 4yi. The I really doesn't matter. I'm more interested in the number in front of it. So I'm going to say that 12 is equal to 4y because I just need the numbers in front of the i's to match. From here, all I'm going to do is basic algebra to isolate the variable and solve. So on this side, I'm going to divide each side by 3, and I get 3 is equal to x. So that's what my x variable equals. On the y side, or the imaginary side, I'm going to divide each side by 4, and I get 3 equals y. So it just so happens that in this equation, Both of my variables are equal to 3. Let's go ahead and do another one. This time, I'm going to have 2x plus 7 plus 3 minus yi, 3 minus y in parentheses I, equals negative 4 plus 6i. So when I tell you that these are all complex numbers, that means they only contain a real portion and an imaginary portion. So on this one, on this first number, my real portion is that entire 2x plus 7, okay, because I don't have any other parts to this, and I already have my imaginary portion here. That will be equal to, then, the real portion from my right side, which is negative 4. With that same idea, it is the entire 3 minus y that's going to be equal to the 6, which is the number in front of my imaginary, on the other side. From here, I just go ahead and start simplifying and solving for my variables. So here I'm going to go ahead and subtract the 7 over. I get 2x equals negative 11, divide each side by 2, and I get x is equal to negative 11 over 2. I need to do the same thing with my y's. So I subtract the 3 over, I get negative y equals 3, which means y equals a negative 3. My next example is somewhat similar to this one that I just did. Here I have a plus 3b plus parentheses 3a minus bi equals 6 plus 6i. Just like before, I only have a real and an imaginary part. So 3a minus b on this first one is my imaginary, which means that the a plus 3b at the front all has to be my real part, which means I'm going to take it and set it equal to the real part from my right side. Same thing with my imaginary. Good news for us, it's already grouped together. So I have 3a minus b from the left is equal to the 6 from the right. So this one is a little bit different because I don't just get one variable in each of these equations. I actually have 2. So this is a system of equations with 2 variables, which here are a and b. And I'm going to have to use some of that information I've done before and some of those skills to solve for a and b. As it's looking right now, I'm probably going to go ahead and do elimination with the b's getting canceled out because this one's already positive and this one's already negative. So all I need to do is make this negative b into a negative 3b by multiplying all 3 terms by 3. When I do that, I get 9a minus 3b equals 18. Just so they're close together, I'm going to go ahead and bring down that top equation as well. For elimination, I add straight down. The b's cancel just like I wanted them to. 9a plus a is 10a. 18 plus 6 is 24. So I get a is equal to 24 over 10, which can reduce to 12 over 5. So I've gotten my a. All I have to do now is take that a and plug it back into one of these equations and then solve for my b. I'm going to go ahead and plug it in to this 3a minus b equals 6 equation, which leaves me with 3 times 12 over 5 minus b equals 6. I need to go ahead and multiply that 3 in. When I do, I get 36 over 5 minus b is 6. Subtract the 36 over 5 over. I would like to put 6 and negative 36 over 5 together, which means I'm going to have to rewrite 6 as a fraction over 5. I recognize that this is the same as 30 over 5 because 6 times 5 is 30. 30 minus 36 gives me a negative 6 over 5. And when I divide by the negative, I get b is equal to a positive 6 over 5. So I'm out of time. The rest will be on the next video.